YouTube. In this video we're going to be solving more trig equations, but we're going to focus in this series of videos on trig equations involving multiple angles. And so you'll notice that I'll go ahead and start with this one that we see right here. When we solve trig equations, we say we have some angle that we're looking for that when we plug it back in that would satisfy this. And what we're looking for is some angle between 0 degrees and 360 degrees that when I plug it back in here would make this one in particular true. But you'll notice that we have a 2 inside here with our angle. So what we're used to seeing in the past are equations that look like this: cosine of theta equals root 3 over 2, and our method for solving this was just to do the cosine inverse of both sides. We say cosine inverse of this would leave us with just theta, where if I did cosine inverse of the right, I'll write that down here, I get this thing right here. And we can check this on a calculator, and we will. But the idea here is we're going to do the same thing. So in terms of how I would do this, step 1 is going to be this: isolate the function. Okay, so in this instance here, when I say isolate the function, I mean let's get cosine of 2 theta by itself. Now I notice that this isn't 2 cosine 2 theta or anything like that, or cosine 2 theta plus 4, where you have to subtract 4 from both sides. We already have this thing by itself. So number 2 is going to be this: use inverse trig functions. So inverse trig functions to undo the trig function. Okay, and so the idea is that once we have this undone, we'll have what's on the inside of it here. So what we're going to do is we're going to do this. We're going to take the cosine inverse of both sides. This is just me showing my work here. So very similar to what we've already done with trig equations. These would cancel out. The only difference now is this: we get left with what was on the inside, which is 2 times theta, and on the right side here we have cosine inverse of root 3 over 2. So our job is going to be now to evaluate this and find the angles that cause this to be true. So angles. So we're going to say use reference angles to find the original angles in standard position. Okay, so let's go ahead and do this, something that we're already used to doing. I'm going to go ahead and type this into my calculator here. We're going to say cosine inverse of root 3 over 2. So now I have a very not desirable calculator, but I can do this. I can say 3, the square root of that. We're going to take that divided by 2. And so I get root 3 over 2, and it's positive. I'm going to do the cosine inverse of this. So I'll hit my cosine inverse key, and we're in degrees, so I get 29.999999. As a matter of fact, this comes out to be a 30-degree reference angle. So what this means here is this: we have a theta hat of 30 degrees. And so sketching this out to conceive of it, what we're saying is I've got 4 angles, each with a 30-degree reference angle possibly. And so we'd say each of these is 30 degrees. And we say that we also know where our trig functions are positive or negative using all students take calculus. So we said we were talking about cosine being positive, and if cosine is positive, that means we were either in the first quadrant or the fourth quadrant. So our 2 angles here are these. We say 30 degrees, not a very good drawing right there, or we say 330 degrees. So the way this problem works is very much like we've done in the past. We're going to find these 2 angles right here, but then we're going to have to solve for them individually. So a few things that I want to say about this. We found out that 2 theta equals cosine inverse of this, which means that 2 theta equals 2 different things. 2 theta equals both 30 degrees, and it equals also 330 degrees. So we're going to do something a little bit interesting here on this problem. But we wanted to find all answers between 0 and 360 degrees that satisfy this, and also check this graphically. So now, knowing what we know, we are going to add in a few things extra on this one. We're going to put in, first of all, plus 360 degrees times k. We know that if we were to go 360 degrees and add that onto this angle right here, it would just be coterminal with that angle. So really what this means is plus any angle that's coterminal with this. And what we're going to do now is we're going to isolate the theta by dividing both sides by 2. We're going to talk about what it is that we just discovered here. So we say theta in the first instance here, theta is equal to half of 30, which is 15 degrees, plus half of 360, which is 180 degrees k. I'm going to put that in a box, and that's one of our solutions. And then we say down here we get theta is equal to half of 330, which is 165. You can check that on a calculator, plus 180 degrees k. Okay. So now what I want to do is I actually want to interpret this graphically, which means what we're going to do is we're actually going to go graph the graph y equals 2, or sorry, cosine of 2 theta, And we're going to set that equal to the graph of y equals root 3 over 2. So I'll tell you what, I already went and graphed y equals cosine of x. What I wanted to do was really graph y equals 2 cosine of x. And you'll notice that this is our normal cosine curve. It starts up at 1, goes down to -1, and then back up to 1 again in a 2 pi period. We know from studying graphs of these already that when we put a 2 in here, all that does is it sends it through 2 cycles in a normal 2 pi period. So we have y equals cosine of 2 times theta, or 2 times x. And in this case, we want the square root of 3. Take that, and we're going to divide that by 2. And this equals some new function y. Okay, so here's what we're seeing here. What we're really asking is, what are all the x values that would cause these two graphs to be the same graph? And from a 0 to 2 pi, or 0 to 360 degree interval, we can see that these two graphs, they run into each other here, 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 and here. So our job is to find all 4 of these angles that do this. Okay, so the way this looks is we certainly got 2 answers right here. And just looking at this, we would say, okay, well, my 2 answers happen to be, let's write them out. We say theta equals 15 degrees was one of them, and 165 degrees was the other. And technically, when you go look at the graph, we say 15 degrees, that is pi 12ths radians. So we say 15 degrees, and also 165 degrees, which is this 11 pi 12ths, which, by the way, 165 is right before this pi right here, which is 180. So these are both reasonable. But we also have to describe these 2 solutions as well. So the way this works is we are going to plug in values for k, starting at 1. Okay, so we say let's plug in k equals 1 into both of these equations, and we would have gotten 15 degrees plus 180 degrees plus k. We get a 15 degree plus 180 degrees times k, which is 1, which is really 15 degrees plus 180 degrees, which is 195 degrees. So we also get 195 degrees as a solution because it's between 0 and 360 and satisfies this. And we also say, what if I plugged in 1 for this k right here? I'd get 165 degrees plus 180 degrees times 1. So this would really be 345 degrees, 345 degrees. Now I noticed that we did all of these in degrees, but I also say, looking at my graph, this is reasonable because we could say that this is just beyond 180. This is our 195 degree angle where these two graphs are equal. And this is our 345 degree angle right before 360 degrees here. So we're going to try this again and just kind of hammer down this process. But basically it says, let's go solve this angle with multiple angles and list your answers in radians between 0 and 2 pi. So we would say, okay, well, first thing I want to do is I want to get the trig function by itself, which I notice I already have. So since I have sine of 2 theta by itself and equals -1/2, what we're going to do is we're going to take the inverse trig function of both sides. So we'll take sine inverse of everything on the left, sine inverse of everything on the right. These cancel out and we're left with 2 theta. 2 theta is equal to sine inverse of -1/2. So now what we need to do is we need to go find what this gives us as a reference angle. So we say -1/2, that's 0.5, and it's negative. We want to do the sine inverse of this, and we get a 30-degree reference angle. As a matter of fact, we'd say this right here gave us a reference angle of 30 degrees. So we're going to go sketch this out. We say 30, 30, 30, 30. These are all congruent, and they're all 30-degree reference angles. Knowing that all students take calculus, where our trig functions are positive, it gives us this mnemonic right here. We say that we had a sine value that came out to be negative, so we must be either here or here. So we say our two angles are 30 past 180, so this is a 210-degree angle, or 30 shy of 360, which this is a 330-degree angle. So we'd say two things we could say here. We could just say that instead of theta equals 210, we say 2 times theta equals 210. And instead of saying theta equals 330, we'll say 2 times theta equals 330 degrees. Let me fix that. 330 degrees. So a couple other things. We are going to tack on plus 360 degrees k. Get in the habit of doing this. And we say, okay, now let's divide everything by 2 to get just theta. So we say theta equals half of 210 is 105 degrees plus 180 degrees k. And we say over here, dividing everything by 2, we get then theta must be equal to half of 330, which is 165, plus 180 degrees k. Okay. So we say, all right, well, what are our angles between 0 and 2 pi or 0 and 360 that give us this? Well, we have 2 of them right now. We say 105 and 165. But what I know is if I were to put in 1 for k right here and 1 for k right here, we would say I'd get 105 degrees plus 180 degrees times 1, which is 105 plus 180, which is 285 degrees. And if I were to say plug in a 1 for k over here, I get 165 degrees plus 180 degrees times 1, which is 180. And adding these together, we get 345. So these are all the angles between 0 and 360 degrees that satisfy this equation up here. The only thing is that now we'd want to go back and list this in radians. So we could take each of these values here and actually just take them times pi over 180. Cheers.